Stainless steel tubes are often used in applications that require rigid materials for potable water conveyance. Manufacturers select stainless steel because certain man-made materials have unwanted or unknown exposure effects, while stainless steel has many desirable qualities for maintaining clean water. Steel tubes can also be used for structural support in buildings and vehicles. Manufacturing steel tubes. There are three main methods of manufacturing tubing that lend their names to tubing classifications. Seamless. Seamless steel tubes are produced through extrusion. Extruded tubes can be formed in a hot or cold process. Long sections of steel bar are forced through a die that blocks out the intended shape of the tube. Electric-resistant welded. ERU. This method involves passing a rolled sheet of steel through two weld rollers. The weld rollers have a groove around their circumference, through which the steel roll passes. There is a contact at the roll seam that transmits electricity at a high enough current to weld the seam closed. The resulting weld is very small. Drawn over mandrel. DOM. A mandrel is a small piece of metal inserted into the tube to define a shape. It gives the tube extra support to prevent unwanted wrinkling during drying. The tube is passed through a die that has a smaller diameter than the current tube size. As the tube is drawn, it shrinks to match the size of the die's diameter. This process allows for tight tolerances and specifications. Each of these manufacturing processes allows manufacturers the ability to form varying tube shapes and sizes. Tubes are not always cylindrical and can be made in triangle, square, or other polygonal shapes. Steel tubes destined for certain applications require extra processes as well, such as tube laser cutting. Generally, a steel tube manufacturing process is chosen for its interaction with the type of steel to be used. Certain types of steel react poorly to heat because of carbon content, so they can't be easily welded. Steel types also play a role in decisions regarding use in volatile applications. Stainless tubes applications. Steel tubing is used in high numbers in plumbing applications. The reasons are threefold. 1. Stainless steel is very sturdy, composed of 80 to 90% steel and 10 to 20% chromium. Steel tubing can handle the types of pressures exerted by water upon plumbing structures. Additionally, the surface of stainless steel does not allow for much adherence by particles or bacteria, so purification processes will not pass on unintended detritus. Finally, steel does not contaminate drinking water. Steel tubes are also used in a wide variety of structural applications, such as industrial and residential construction. Examples include fences, gates, railings, playground, and athletic equipment. Steel is often used for construction tubes over other metals like aluminum when extra stress resistance is necessary. Steel tubes can also be used in automotive applications and even as parts of furniture. Seamless steel pipe production process. Starting with solid steel bars that are cut into precisely weighted billets, they are then loaded and heated in a natural gas-powered rotary furnace and fired until they reach a temperature of 1200 years, 21,280 degrees Celsius. The steel then moves to a barrel-type piercing machine to turn the material into a hollow expansion. This is achieved through a process known as efficiency management. Next, the hollow expansion goes into a high-quality finishing mill to be stretched. Then it is pushed into an induction furnace to reheat to a uniform temperature before being sent to the relaxation mill, where the outside diameter of the tube is reduced to suit the specific needs of the customer. The second important step is the heat treatment process, which ensures the hardness and toughness of the steel pipe. Starting from the furnace, where the pipe is heated to a higher temperature, it then enters a cooling process where water injection is used to accelerate the pipe from about 900 degrees Celsius to ambient temperature, causing rapid phase change in the steel. As a result, the steel tube is very strong and brittle. So the tube is then reheated to a temperature below its transformation temperature in a quenching furnace to restore the steel's ductility and adjust the mechanical properties to reach the required range. The tube then moves to a resizing machine to achieve the required dimensional tolerances before straightening in the straightening machine. The final straightening needs to be an oval shape achieved so that the tube is in its final state before being inspected. Check and check. Finally, here the automated line carries out rigorous testing and verification to ensure the steel pipes meet the quality level and specific customer requirements. Hydrostatic testing is first performed to ensure that it will meet the specified pressure requirements before being subjected to electromagnetic testing to detect internal and external defects. Ultrasonic testing then uses high-frequency sound energy to measure pipe wall thickness. It is then faceted and chamfered to help begin the threading process while threading the pipe. The tube remains in a fixed position when an automatic rotating head operates. All threads are then visually inspected and size controlled automatically by status. Then, modern testing equipment, specialized automated equipment, will be used during the joining and makeup process to obtain the final pipe and joint connection. Next, drift testing is performed. Check to make sure there aren't any blockages in the pipes. Now, the pipes are lacquered or varnished to prevent corrosion during storage or transportation. Then weight measurements and stencils are made to identify each pipe based on temperature and number of pipes, including all marking requirements to comply with tube marking technology. Finally, the tubes are automatically packaged and ready for delivery to the designated service center, ready for distribution to customers. This state-of-the-art facility creates pre-tested tubes from a single block of steel. Electric resistance welding steel pipe production process. Electric resistance welding, aero-welded pipe, is used to transport oil, natural gas and other vapor and liquid objects, which can meet various requirements of high and low pressure, and currently occupies a pivotal position in the field of transportation pipes in the world. The electric resistance welding pipe is manufactured by cold forming a piece of steel plate into a cylindrical shape, and then passing an electric current between the two edges of the steel plate to heat the steel plate to a point of force, forcing these edges to form a weld that was not initially used to fill the material, but use low-frequency alternating current to heat the edges. This low-frequency process has been used from the 1920s to the 1970s. In 1970, the low-frequency process was replaced by the high-frequency aero pipe process, which produced higher quality welds. Over time, it has been found that the welds of low-frequency aero pipes are susceptible to selective joint corrosion, huck cracks, and insufficient joint bonding. Therefore, low-frequency aero is no longer used to make pipes. High-frequency processes are still used to make pipes for new pipeline construction. Resistance welding can be divided into resistance welding and induction welding. The aero tube is cold formed into a cylindrical shape rather than hot formed. Use electric current instead of flame to heat the edges of the strip for welding. The rotating copper disc is used as an electrode, which can raise the temperature to about 2,600 degrees Fahrenheit for effective welding. Unlike longitudinal submerged arc welding, aero usually uses alternating current with a frequency of 100 to 800 kHz, or 100.000 to 800.000 cycles per second. This process is characterized by two effects: the skin effect, or the concentration of high-frequency current on the surface, and the proximity effect, when the high frequency is concentrated on two adjacent parallel inner edges in the welding wedge before the welding point. These effects minimize the heat released during the welding process. Therefore, the structure of the basic material changes in a relatively small area around the fusion line, the center of the weld. Use a scraping device to remove the molten material on the inside and outside of the weld. There are several different types of ARI, but the most common type is resistance spot welding. In resistance spot welding, 2 electrodes are used to apply pressure and current to the weld joint. The electrodes are typically made of copper or a copper alloy, and they are cooled by water to prevent them from overheating. ARI is a versatile welding process that can be used to join a wide variety of metals, including steel, aluminum, and brass. It is a fast and efficient process that produces strong, high-quality welds. ARI is commonly used in the automotive industry, appliance manufacturing, and construction. DOM production process. Drawn over Mandrel. DOM, round mechanical tubing, is a cold-drawn 1020 by 1026 electric resistance welded tube with all the flash removed prior to cold drying. In comparison to another tubing, DOM round steel tubing is produced to more exact OD and ID tolerances and has the highest weld strength possible. The manufacturing process for DOM round steel tubing begins with coils of steel, which are slit to the proper width for the desired tube size. The strip is cold formed and passed through an electric resistance welder, which joins the edges together under pressure to complete the tubular shape. After testing the weld's integrity, the tubing is cut to length for further processing. The cold drying process creates a uniform, precision product with substantially improved tolerances, surface finish and tensile strength, increased hardness, and good machinability. In this process, the tube is cleaned and annealed, and one end of each length is squeezed to a point so it can be gripped by the drying mechanism. The tube is then drawn through one or more dies and over mandrels. This reduces the diameter of the tube and thins its walls to the required dimensions in a controlled fashion to provide the qualities desired in the finished product. Metallurgically, drying improves the tube's concentricity, tensile strength, hardness, and machinability. Close dimensional accuracy is achieved through tight control of both outside and inside diameters.